Power electronics components have become one of the most important building blocks for modern electronic systems used for driving electrical motors or for converting energy from AC to DC or vice versa. Their consistent operation influences the reliability of the final application, such as the drivetrain or braking steering system of an electric vehicle. The power testers was designed to address thermal challenges of semiconductor components and modules such as diodes, IGBTs, silicon and silicon carbide MOSFETs. It offers both high-fidelity thermal characterization capabilities to understand the device thermal performance and active power cycling to help estimate the lifetime of a device. When performing these in an automated combination, the result is useful data on lifetime and failure mechanisms from a single test sequence. Analysis and thermal simulation are supported by a thermal model generated by the test and represented by the so-called structure functions. These can also describe performance of important structural layers inside the device and help locating structural thermal failures. My name is Zoltán Sárkány. I am a product manager responsible for the design and development of Siemens Simcenter POWERTESTER series of products. We offer different versions of the measurement station covering device ranges from 10 to 3600 amp of current. In the next few minutes, I'm going to show you the operation of the Simcenter POWERTESTER through a measurement example. The system we are going to review today can output maximum 2400 amp via 4 600 amp powering channels with output voltage up to 12 volt. The system is capable to test up to 16 devices. 4 of these devices are connected in series on each of the 4 heating current outputs. Measurement current is available for each heating current outputs and dedicated gate drive output is available for all devices. This power tester contains no cold plates or closed measurement space. It is built into a 19-inch rack, which allows minimal system footprint and facilitates simple connection to external measurement environments. The system has a dedicated serial communication interface to connect the chiller, to provide regulated coolant temperature and carry out automatic temperature sensitivity calibration. The high current operation, of course, requires dedicated safety sensors and mechanisms that allow autonomous operation without constant supervision and provide alarms or even shut down the power tester in case of critical safety events. There are dedicated safety sensor inputs available, so you can connect it to your measurement environment and set it up in the control software. The system has built-in control computer and provides easy-to-use touchscreen interface for easy operation. This covers the full workflow from the device definition to the actual RTH measurement or power cycling. The system's primary application is testing silicon and silicon carbide diodes, IGBTs and MOSFETs. Let me show you the measurement workflow for two 2400 amp IGBT devices connected in series. These devices have a classic package with flat cooling surface. We are going to use a cold plate with universal screw fixture to attach the devices. These packages contain a single IGBT transistor each. We are going to connect all the 4 heating current outputs in parallel to supply the required heating power. The high current connections and measurement current cables need to be attached to the top and bottom of the device chains. Gate drive outputs and voltage measurement inputs are combined in a single connector to facilitate clean and simple wiring. The color coding of the banana plugs and the labels on the cable ends help in the connections. No other connections like thermocouple or other temperature sensors are needed for the junction temperature measurement. The test setup is organized at 2 levels, devices and projects. Device definitions contain the most important parameters of the test samples, while the projects define the arrangement of these devices and the actual parameters. We need to define a new device for our sample. First, the measurement mode has to be selected. In the current example, the IGBTs are heated and measured in saturation mode with a constant gate emitter voltage applied to turn on the devices. Then, a few important parameters like maximum load current need to be defined, which are easy to be filled based on the device datasheet. As temperature is captured by an electrical measurement, the accurate temperature sensitivity information is essential for calculating the junction temperature from the measured voltages. The system also provides the option to import or simply type in the temperature sensitivity value. Here we need to define the gate voltage and sensing current parameters for each device, the desired calibration temperature range and step size. During the temperature sensitivity calibration, the system automatically controls the chiller temperature and captures the device voltage as a function of temperature. At the end of the process, you can select what type of fitted curve to use for the transformation. Linear or higher order polynomial or exponential functions are available. Once we have the DUTs calibrated, it is ready to be used for thermal transient testing or power cycling. For this, we need to create a new project. We need to give it a unique name, select the appropriate channel configuration to handle all 4 outputs together as one 2400 amp current source and assign the device we previously created. Thermal transient measurement can be initiated by selecting the Setup RTH measurement function. The desired heating current level and the measurement timing parameters need to be filled. You can freely configure heating and cooling time. By clicking Continue, the measurement will start. First, the system heats up the device. Then, after the set heating time, the heating is turned off and the thermal transient is measured. You can view the preliminary results on the power tester, but the actual post-processing shall be done on a separate PC on exported results. The thermal transient curve measured by the system and the structural information extracted with the post-processing of the captured data can be utilized in various ways. Standard thermal metrics provided in datasheets like junction to case or junction to coolant thermal resistance can be created or verified utilizing the transient dual interface method. By repeating the same measurement with two different thermal interfaces or flow rates, the two thermal transient curves will overlap until the heat reaches the changed interface. The desired thermal resistance can be read at the divergence point of these two curves. The extracted thermal RC network can be used to generate a compact thermal model for simulation purposes or serve as a reference for the fine-tuning of detailed 3D thermal model parameters. The resulting model will serve accurate temperature not only in steady state but in time-dependent simulations as well. Finally, the structure function model can help understanding the thermal performance of various structural layers inside a package, compare different technologies or process parameters, and hence optimize packaging technology. The main function of power tester systems is to carry out power cycling tests combined with RTH measurements. The system is capable of automated power cycling compliant with current automotive qualification guideline AQG 324, but provides control and monitoring functionalities beyond the standard requirements. The integrated thermal transient measurement capability enables repeated, non-destructive structural analysis throughout the power cycling process and automatically follows the degradation of various structural layers inside the package. Basic test parameters like heating current and timing parameters need to be defined. We can configure the automated thermal transient test and optionally gate current measurement feature as well. There are various cycling control strategies defined in the control software. I can select how the system shall regulate the powering parameters with the device degradation. Current testing guidelines prescribe using fixed heating current independent of the device degradation to best mimic the real usage of the components, but there are optional methods to ensure constant junction temperature change or constant power step by regulating the heating current or gate voltage as well. Finally, the cycling stop criteria needs to be defined. The system monitors several parameters in each cycle, and if they exceed a certain threshold, the cycling is stopped automatically. Once the power cycling started, it will run automatically for days, weeks, or months until the set maximum cycle number or another cycling stop criteria is reached. One of the most important output of the power cycling test is the component lifetime, the number of cycles elapsed until the failure of the device. This information can be used as input parameter for lifetime model fitting or ultimately lifetime calculation based on mission profile descriptions and simulations. However, the additional parameters such as on-state voltage, gate current, and thermal resistance measured and monitored throughout the power cycling test are essential in verifying that the failure mode observed during the cycling matches the experiences in real-life conditions. Moreover, the thermal transient test results and the generated structure functions can help understanding how the structural defects develop. It can be used to identify root causes of failure and weaknesses of the structure and hence providing useful feedback to the development. Throughout the cycling progress, the status of the test and all important parameters can be monitored on the main touchscreen of the system or remotely using the web interface.